Okay, let's start in chapter 24, carbonyl condensation reactions. We're going to start with the Aldol reaction. Note Aldol is not named after anyone. Its name, I believe, originally comes from the fact that the product is a combination of an aldehyde and an alcohol, as we will see. Although it turns out that the Aldol reaction is useful for ketones as well as aldehydes. All right, so what we need, or what's going to happen here, is we're going to form a beta-hydroxycarbonyl compound in the presence of base, and we usually use hydroxide. So here's an example of the Aldol reaction where you take two equivalents of your aldehyde and you add base to it, and you end up with this beta-hydroxycarbonyl compound where you've got the aldehyde at this end, the CH2 here bonded to a carbon OH and a CH3 here. Let us examine where these parts come from. This right-hand part here of the aldehyde here is this part of one of your equivalents of aldehyde. This CH2 is this carbon with two of these hydrogens still attached. Your second equivalent of aldehyde, the carbonyl of your second equivalent of aldehyde, becomes this carbon OH, this alcohol here. And the CH3 here, the methyl group, is this methyl group here. So let's look at the mechanism of this reaction. Recall that we've got a alpha carbon, has hydrogens on it. Recall the pKa of these guys is roughly 19. And so if you have hydroxide, a base, note hydroxide isn't a strong, or it's a strong base, but the pKa of the protonated hydroxide is water, pKa of 15.7. So this reaction is an equilibrium reaction, and truthfully kind of lies to the left here. So this reaction, yes, you will make some of this product where this hydroxide will come in, snag that hydrogen, and make this enolate. Well, we saw that in last chapter. We realized this is the thermodynamic enolate product. And this will occur, just the equilibrium tends to lie to the left for this step. The deal is, however, that after you make this enolate, this carbanion can attack the carbonyl of the second equivalent of aldehyde. And we've seen this before. This is just nucleophilic attack on an aldehyde. The pi bond breaks, lone pair goes up here. So we've got this alkoxide type beast. Protonate it with water, and this becomes the alcohol, and this aldehyde is now attached to this carbon in that CH3, and you end with that product. And if this product is stable, even though this equilibrium lies to the left, the fact is that this will react and create this, which will create this product here. And if it's more stable, the equilibrium of these steps drives the whole reaction to the right. Good old Le Chatelier. All right. Some things to note with this reaction. First of all, the first step is the catalyzed enolate formation. Equilibrium favors reactant, so only a small amount of enolate is going to form, which means if we only have a small amount of this enolate formed, you've got plenty of this aldehyde left to react with. For stoichiometry purposes, we put the 2 in front of here because we can see that our product is going to have 2 of these original aldehydes hooked together, so you need the 2 in there for stoichiometry. When you're running the reaction in the lab, it's not like the reaction doesn't start until you add the second equivalent of aldehyde. You have that aldehyde in there, you add the base, the reaction is going to occur. All right. And when we look at the overall equilibrium, what we find out that with aldehydes, overall equilibrium favors the products. This product here tends to be more stable than the original aldehydes. However, ketones, they favor the reactant. This carbonyl, recall with 2 R groups on here, this carbonyl is a little bit more stable, not as easily attacked, so ketones, we favor the reactants. But we can still use good old Le Chatelier to push the reaction to the products. So what would happen then if we took 2 equivalents of this cyclohexanone and added base? Well, base will attack the hydrogen alpha to the carbonyl, make that a carbanion. This carbanion will attack the carbonyl of another one of these cyclohexanones. Recall, the base attacks the first cyclohexanone to make the carbanion. The carbanion attacks the second carbonyl to change this into the alcohol. Note, make sure you count your carbons. The most common mistakes that people will make when they're drawing the product is to forget that this carbon is bonded to this carbon. You have to have a bond between this carbon and the carbonyl, formerly carbonyl carbon. Some people will just make this carbon and this one the same one, and you've lost a carbon if you do that. So make sure you're counting your carbons. Okay. As it turns out, that reaction goes pretty well, but another reaction that happens, oftentimes we can't help it, is that aldol product will dehydrate. All right. These beta-hydroxycarbonyl compounds tend to easily be dehydrated under basic conditions. Recall that normally, 2 things. Normally, if we're going to dehydrate an alcohol, we put it under acidic conditions. Remember, acid catalyzed dehydration of an alcohol. Turns out, beta-hydroxycarbonyl compounds can dehydrate under basic conditions. That's the first thing. Second thing is, recall from our aldol reaction, the catalyst is base. We have a base catalyzed reaction, which means we get hydroxide back at the end of the reaction. Therefore, we usually have base around to do this dehydration reaction. So what will happen is our normal reaction, if we take 2 of these guys right here, acetaldehydes, run our reaction, we'll make this beta-hydroxycarbonyl compound a little more OH. We're going to dehydrate it. We're going to take off this OH and that hydrogen to make water and form a double bond between these 2 carbons. So that's the end result, is you've got carbonyl, single bond to a CH, double bond to this CH, single bond to this CH3. Note, this carbon right here, the end carbon of the double bond, was once the carbonyl carbon of an aldehyde. All right, and note, yeah, you're looking at this is an alpha-beta unsaturated carbonyl compound. Okay, so another way to look at it here is the carbon double bond oxygen has now become a carbon double bond carbon to the other molecule. These reactions tend to go, if you had this very molecule right here, you might have to bump up the concentration of base to get that to go. But remember, alpha-beta unsaturated carbonyl compounds are fairly stable because you have conjugation. Double bond, single bond, double bond. If you can add more conjugation to it, recall from earlier chapters, the more conjugation you have, the more stable the molecules are. So if you can have more conjugation, this dehydration product will just occur. For example, this is the product that we're going to make. If you took 2 of these molecules right here, a ketone with an ethyl on one side, a phenyl group on the other side, you add OH minus, typical mechanism. You're going to snag a hydrogen here, just in case you're worried. There is no hydrogen here, so you don't have to worry about that. Snag one of these hydrogens to become a carbanion. This carbanion will attack another one of these guys at the carbonyl carbon, and you will make this beta-hydroxy carbonyl compound. Note, though, that if this dehydrates with base, this OH, this H will be gone. We'll make this compound, and note, all these carbons are sp2 hybridized, carbonyl carbon sp2, 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 sp2. You have now then conjugated all of these carbons together. This phenyl ring is now conjugated with that phenyl ring. That makes this a very stable molecule. Because it is so stable, these groups will just dehydrate on their own. You pretty much cannot stop this product here. You cannot stop it from dehydrating. It will just do it because the product's so much more stable. All right. But in this example, note we didn't have to worry too much because we only had this carbon here with hydrogens on it. There were no alpha hydrogens on this carbon, this alpha carbon over here. So this base could only attack those guys. What if that was not the case? Well, if that's not the case, we have what we call a crossed Aldol reaction. Okay. What if we started with this? What if we mixed this aldehyde and this aldehyde over here? A different aldehyde or two different ketones. And we threw in base. Well, what could happen? Well, one could imagine there are four possible reactions that could take place here. The hydroxide could snag one of these hydrogens, and this carbanion could attack that carbonyl. So that would give us one product. The hydroxide could attack one of these hydrogens to make this carbon the carbanion, and that carbanion could attack this carbonyl over here. That's two products. However, the hydroxide could attack one of these carbons, one of these hydrogens, making this carbon the carbanion, and it might just happen to run into another one of these acid aldehydes. So it will attack another one of itself and make a fourth product, and by the same token, this carbanion could attack another one of these guys and make a fourth product. So this one could attack this, that's one product. This could attack this, two products. This could attack itself, three products. This could attack itself, four products. And you can get all four of these products. And since there's not a lot of conjugation, you might have to push it a little bit, add a little bit more base to get them to dehydrate, but you get all four of these beta hydroxycarbonyl compounds. That makes this not synthetically useful. But what if we then say, okay, but let's recall our lesson from up above where you only have hydrogens on one side of the carbonyl. So what if we had benzaldehyde here? And we had acid aldehyde. If we add base, note there's no carbon with hydrogens on it, alpha to the carbonyl. This is the aldehyde hydrogen that doesn't get involved in any of these reactions. So our acid aldehyde is the only reactant here that has hydrogens on carbons alpha to the carbonyl. Therefore, this is the only one that will become the carbanion. And if we play our cards right, we can get it to attack this carbonyl over here. Truth is, yes, it may attack itself, but there are things we could do in the lab with concentrations to make sure that this carbanion was more likely to see this aldehyde, so that this is the major attack we get here to form this guy here, this beta hydroxycarbonyl compound. Note that if we dehydrate, recall we always dehydrate alpha to the carbonyl and beta to the carbonyl to make the double bond here. If you do that, then you've conjugated this benzene ring with that double bond with this carbonyl double bond here, so we don't even have to worry about this. This product will be the only thing we see. And if we look, this is benzaldehyde, acid aldehyde. We end up with cinnamaldehyde. Wouldn't that be a lovely lab to do one day? All right. Now, this cross aldol can be especially effective if we use something that has very low pKa alpha carbon hydrogens. Whoa, remember this ester right here? CH3, CH2, O, C double bond O, CH2, C. Yeah, recall the pKa of those two hydrogens right there? Weren't pKa of those two about 9? Which means if you put in this guy right here, our malonic ester, and you also put in this ketone right here, and added some base, at first one would say, oh no, we have a ketone, we add base, couldn't we get this guy deprotonated and this guy deprotonated? Truth of the matter is, if you add base, these two have pKa's of roughly 19, these two have pKa of 9. So the base will always take one of these guys and make this a carbanion. So this will be the only carbanion we will get, and it will only attack this carbon right here, because when we add our base to this guy, we can strip a proton and make all of our malonic ester as the carbanion, because the equilibrium for this molecule reacting with base lies to the right. So all of this will become the carbanion. This will be the only carbonyl left in solution to attack, and we will get this guy right here, which will dehydrate, because when this dehydrates, note this looks a little funky. Here is our malonic ester that we made the carbanion. Here is this aldehyde, or this ketone that got attacked. But when it dehydrates, we then conjugate the double bond from our dehydration with these two. Note sp2, 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 sp2 hybridized. This is a conjugated system, so we will get that almost all the time. All right.